Hi everybody, welcome to Climate Change Calculated, this time a special about the corona COVID-19 virus. Okay, so everybody knows the coronavirus is capturing the world since the start of this year, right? So, and it's interesting in this context is that it's likely to be just another symptom of climate change. So I looked at this paper from the Scientific American, and there they say, some experts believe climate change, along with other environmental disturbances, could help facilitate the rise of more brand new diseases like COVID-19. So all the change in the environment, moving species, changing temperatures means we also have new combinations of viruses and beings, and this leads to evolutionary changes, basically creating new viruses. This is basically evolution in action. So another interesting aspect is even if it does turn out to have some seasonal components in the future, that effect will likely be small this year, experts say. I also looked at the data of COVID-19 for the southern hemisphere and found that there seems to be the same speed of growth as in the northern latitudes. So this confirms it. So this also comes at the same time as the catastrophic Australia fires and record temperatures on the South Pole and melting of the South Pole. So here's a link to it from New Yorker magazine, and here it says Antarctica's Esperanza Peninsula reached 65 degrees Fahrenheit, the warmest ever. Right, so Antarctica begins to warm. And about 100,000 years ago, the melting of the West Antarctic, so just part of the Antarctic, ice sheet produced all by itself 6 feet of sea level rise. Right? And it took less than 2 degrees Celsius of warming to melt it. And we are currently at about 1.1 degrees of warming. So this is also what we saw in my earlier parts on climate change. And we are heading almost inevitably for 2 degrees. Right, so that's what they say. And so this also shows another risk of climate change. So this warming that we already have already comes close to melting the West Antarctic, and hence 6 feet sea level rise. And a quarter of the country's Australia forests have been incinerated in a single bushfire season, as have more than 1 billion of Australia's animals. So that all just happened and is still happening. So this should be a reminder of how dangerous global climate change is for our human civilization. And it also shows the danger of inaction. We need to do something, otherwise we have much more of this. So now let's go to the model of the spread of COVID-19. So I found it actually quite interesting to make a model for it, because you can nicely model it using exponential functions, or what I did here using a logistic function. And for this model, I assume the worst case, that everything continues as is, with no effective countermeasures. So again, this shows the danger of inaction. So it should be a warning about the dangers of inaction. But hopefully we'll not come to this, because we already have countermeasures like canceling meetings of people. And here I'm just not looking at the medical side, but purely at the mathematical, statistical side. So this is for people who are interested in numbers, right? For people who like numbers. So I'm looking at the numbers here, the statistics, fit a model, and then use that model to predict the future. So the spread of a virus is actually a good example of exponential growth, at least in the beginning, right? But when it reaches the carrying population size, it saturates and growth slows. right? If a virus has enough uninfected people around, it can spread, but if it doesn't, then it doesn't spread anymore. If, for instance, everybody is already immune, then that doesn't work. So both phases are actually captured by the so-called logistic function. So you can read more in this Wikipedia link about it, in this section about modeling population growth. And this is the corresponding formula. So simple enough, you just need to know what to plug in here, right? So it turns out that this R corresponds to the factor of increase from day to day. So factor increase is the factor of case increase from day to day. And we need to take the log of it to make it, to basically translate it to this exponential function. K, this K, is the carrying capacity, or the population, the full population. So in our case, all of Germany, 83 million people, or 83E6, as you would write it in the Python programming language, for instance. And P0 is some starting value at t equals 0. And t is the time. So in our case, t would be the number of days, right? So t gives us the time axis. So now we have actually quite a nice formulation, and this logistic function was actually made for this kind of scenario. It is actually made for the population growth and some limit in the growth. So quite fitting. So when we look at the data in Germany, then we observe an increase of about 25% per day, or a factor of 1.25. So we multiply the number of current day with 1.25, and then we know the number tomorrow. And actually, we can estimate this factor, 1.25, by looking at data. So here is the data that I used for it from the Robert Koch Institute. And I actually noted the cases over time, and I noted on March 6 that there are 639 cases in Germany, and on March 14 there are 3,795 cases. So that means 8 days in between. So that means if this factor x is 1.25, then we need, if we want to know x, then we need to have 3,795, resulting if we have x exponentiated by 8, so multiplied 8 times with itself, and then multiplied with 639. So then we can bring 639 on the other side, and then take the 8th root, and then we get x. And when we put this into a calculator, indeed we get 1.25. So that is this number. So this is the day-to-day increase for our data, for our cases. And actually I also looked at data from Australia and Brazil and found that they actually have a similar factor. So this seems to be something more or less common. And since this was in Australia and Brazil, this also means that it will probably not pause in spring, because since this is on the southern hemisphere where they have summer and still continues, then it seems the virus is not hindered by it. So that makes it easy for the computation, but not so good for us. So, right. So actually I used my exponential formula here, starting with 639 on March 6. And then we can simply use this exponential formula here, 639 times 1.25 to the power of t, to make predictions. And t would be the days since March 6. And this formula also works for days before March 6 if we just use negative numbers for t. And I wrote a Python script with these numbers. Here I have this variable factor increase, which is the 1.25. The value on date would be 639, and the day of month is 6 here, to basically get a convenient scaling of the x-axis, of the time axis. And then we can plot the formula for the entire month of March, using the first half for its verification and the second half then for the prediction. So here I have my time axis. It takes the days from 1 to 31, basically the month of March. And here I'm plotting actually now not the exponential model, but the more sophisticated logistic model, which in the beginning actually is identical to the exponential. So it doesn't really make a difference, but here I'm sticking to the logistic function here. So then I let it run. I call my program coronacases.py, and I actually put it in the link to this video so that everybody can try it and also try what happens if we change these variables. So for instance, these variables can be adjusted for different countries, and then you can see what happens for different countries. So this is what we get for the first month, for the first half. So this is for verification. So here we have corona cases beginning from the beginning of March up to the middle, and now we can compare it to the actual cases, and we now can compare it to the data. And I actually found quite a nice link where you have the time axis already here, and then you have the cases, and when you compare the numbers here, it's actually quite a good fit. So as expected, we get a nice exponential curve here. So here you get a few wiggles, as is usual for real data, but altogether we have this shape of this exponential curve. Quite a nice fit. So now we can use this model for predicting the second half of March and plotting the entire March. Right, so here I just extended the x-axis. Now I'm going from 15 to 30. So here is where the first plot ended. So here we have on March 14 we have about 4,000 cases, which is indeed the case in Germany. And now we continue with this prediction, and now we can use this model for predicting what's happening in the end of March. And we can see here in the end of March it reaches around maybe 130,000 cases. So it's over 100,000 cases. So that's already a considerable increase. So can we handle it? For that we have to look at the hospitalization rate. So when we look at this link here, we find that about 15% of the cases need to go to the hospital because it becomes more severe. So not everybody, but still 15% is kind of high. And then 5% need to have critical care. And that's also kind of on the high side here, 5% critical care. So in this case, we need 15% of over 100,000 is actually 150,000 hospital beds, so over 10,000 hospital beds, and 5% of this means 5,000 critical care beds. Right? And when we look at the data, how many beds we have, here you can see it in this link, for instance, in this article. It says we have about 500,000 hospital beds and 28,000 critical care beds. So when you compare it, it's okay. So even if many critical care beds are now used already, it seems 5,000 can be accommodated. So that looks more or less sufficient. But then later, April and May might be a different story. But we come to that in a moment. Because for that we now also need to include the recovery. Right? Not everybody who becomes sick stays sick. Right? Most of them become healthy after a time. And that's the positive part here, right? Not everybody dies, just a few. So we can estimate the time to recovery by looking at the time lag from detecting cases to recovered cases. So again, I'm looking at this plot that I just showed, this time curve. And there we can see that Germany has 46 recovered cases on March 15. So actually I can open it here. So you can see it. It's actually not quite the same as what I showed. So here it opens. It's kind of slow because probably it's used a lot. Yeah, and then you can click on Germany. Yeah, and here you can see 46 recovered, 9 deaths. Now it goes back to the world. So this is where I have it from. So 46 recovered cases. And then we can go back to the time axis that we just saw and see where we had roughly this number on the data for discovered cases. So that gives us a time span. So in this case, we found on February 28, Germany had a similar number, which is 25. So this difference, 28th of February to 15th of March, is 16 days. Right. So we can see it takes about 16 days for recovery, from detection to recovery. So this is also an important number for the further prediction. Because when we take the difference between the active cases, the difference between the detected and subtract the recovered, we get the active cases. Right? So detected minus recovered means they are not done yet. So we can now take these 16 days for recovery to compute the number of currently sick or active cases. So this should be K. From the current cases, we subtract the cases from 16 days ago. And to see significant numbers of recovered cases, we need to look further ahead, say 100 days from the beginning of May. From the beginning of, this should be March, which means early June. So all still assuming there's no effective social distances. So still assuming we have the same rate of increase. So here we can now see two plots. Here is the beginning of March, so here's March 1st, and this is 100 days later, so early June. And we can see here the total number of cases, and here we have the recovered cases. And here we can nicely see the saturation property of the logistic function. So this actually saturates when the entire population is reached. So this might not truly happen. I heard that maybe 70% would be more realistic. But for our case, for our simulation, it doesn't really matter so much. What's more important is this difference here. So here now we have the recovered cases. So here we have those 16 days between those two curves, right? First infected and then recovered. And now we can take the difference and plot the difference. So the difference shows then currently active sick cases. So yeah, from this first case we see that around day 70 we get into saturation, and we get into saturation because basically everybody is already infected, right? And actually we want to avoid this scenario. That's not good. And here is another reason why this is not good. Here we can see the active cases, the currently sick cases, and we can see we have a peak around, say, day 70 or just below 70 at a rate of 6 times 1 to times 10 to the 7, which means 60 million. Right? So this is not good, right? So this is what we cannot handle. So this is what we should avoid. Yeah, so we can see that we get a peak around day 66, which is early May, right? So this is a critical time, but only for the scenario where we do nothing, right? At around 59 million. So if 50% of the active cases require hospitalization, then this still would be, say, 9 million people, and that's much more than we have hospital capacity. So hence it is so important to have countermeasures like social distancing to slow it down, right? You want to slow down the spread. Yeah, so then take a look at mortality rate. So again, we can take a look at the figures from the Robert Koch Institute at this link, and it shows that we had 2 dead on March 9, where we had 2,369 cases, 5 deaths on March 11 and 8 deaths on March 14. So these are very few points. So that makes it actually very difficult to model and makes it very inaccurate. So this is we should take this with a grain of salt. So we can calculate a mortality factor for our model if we assume that it takes about 16 days from discovery to instead of recovery to potential death. So this is the other outcome. Either you're healthy or you're dead, right? And the question is how likely. So the case numbers are now calculated back 16 days. So we start using this data point, 2,369 cases on March 9. So here we have 2,369 and we computed back 16 days using this increase factor. And we get 66.7 cases 16 days earlier. And then of those, 5 now died. So to this date, 5 have died. So 5 out of 66.7, that means 0.07. So that translates to roughly 7%. But this is not the true mortality rate because it also accounts for the undiscovered cases in our model. So this is just to make our curves fit. So the factor to the true mortality rate is actually the underreporting. So if we take this factor and divide it by the true factor, then we get the factor of underreporting. And it's mostly said that we have a mortality factor around 2%. And here we have 7%, so we would have a factor of about 3.5 underreporting of the cases. Yeah, so that also is makes a modeling difficult, this underreporting. So what I did here is I used this factor here for the beginning, the early phases of the spread, to take account the underreporting, and then in the end, closer to saturation, for the long-term prediction, for the 100-day prediction, I assumed the true rate of 2%, because in the end this becomes more precise. Yeah, so here you can also see links to the true mortality rate. Here this says we have it between 2% and 3%. And here this link says it's this range might even be wider, between 0.7% and 5%. Right? But in comparison, the seasonal flu has only 0.1%. So this is an order of magnitude lower than these rates. So this, together with a fast spread, makes it so dangerous. Yeah, so that means for the short-time prediction, we now use our curve for the recovered cases and multiply it with 0.07 to obtain a model for the death cases. And this is what can be seen here. First, for the first half of March for verification. Here you can see the curve and compare it to our few data points, and we can see it's a more or less good fit. So we had 2 dead on March 9. So here we can see we have something like 2.5. Then we had 5 dead on March 13. So here this says we have a little bit more than 6. Yeah. Then we have 8 deaths on March 14. And this actually fits quite nicely here. Right, so this models it more or less okay. Then we can use it for predicting the entire March, which is still using the same model because it's still the early stages. And we can see here it goes above 200 at the end of March. So maybe we get something like 250 dead or so at the end of March. Right, so it should be capital. So now the interesting part, or let's say the more interesting part, the long-term prediction. We can now use our model to predict 100 days after the beginning of March, right? So using now the true mortality rate of 0.02. So this now shows the result. So here again, the beginning of March. Here, day 70, it really rises a lot, and then it saturates here, right? And you can see here we have 1.5 million, so this is about 1.6 million. So we can see after 100 days from the beginning of March in early June, the model predicts accumulated about 1.6 million deaths. So this would be much more than for a seasonal flu. So bad years of a seasonal flu maybe get 30,000 people dead. So this would be orders of magnitude higher. So this is another important number which shows why it's so important to avoid this scenario, right? We need to stop it. And hence I was thinking about a possible solution, and I actually came up with a possible solution. So this is the light at the end of the tunnel now, right? A positive part. So if we could reduce the day-to-day factor of increase from 1.25 to 1.02, which in my model we can easily do by just changing this variable and then let it run again. And I let it run on more days now. Here I let it run on 500 days. And it shows that it would reduce the spread significantly. So here this also means we go from 25% increase to only 2% increase per day. So that's significantly lower. And that's the important part. So then the plot of the currently sick cases, those who require, who are actively sick, would look like this. So here we have, again, beginning of March, and then a year later, 365 days later, we have a start of increase. So here this might be 200,000 people, and 10% would be 20,000. So 20,000 can easily be accommodated by our hospitals. And this 1 year is important because within a year we should have, or we anticipate to have, vaccines. So if we have vaccines, then we can actually stop this altogether, right? And that's the important part here. We can stop it if we have vaccines, effective vaccines. So this would be a possible solution. Delay it until we have a vaccine. And this seems to be the best solution because you can see even here we get pretty high numbers of active sick cases. So just flattening alone seems not to work. We really have to delay it until we have vaccines. So this leads me to my conclusions. It does not have to come to this catastrophe. It just shows the danger of inaction, right? So this shows the worst case basically. Similar to climate change, it shows the danger of inaction. And that's similar to climate change, where inaction will lead to catastrophes of much larger magnitudes. So there should be a 2. So this is basically just a warning shot. If we don't heed it, there is much worse to come. We need social distancing and other measures to slow it down, to reduce the day-to-day factor of increase. So 2% seems to be a solution. And finally, the virus will be with us until we have vaccines and medication to fight the virus. So, yeah, I hope I showed you that this is a serious thing, but we can also do something against it, and it's not hopeless. Right? So, until my next video, like my channel, try out my Python program, and then see you next time.